In this activity, we're going to download some data from Canvas, upload it into StatCrunch, do a linear regression, and then use that information to review some important vocabulary from Chapter 3 that we need to know in order to move on to the inference for regression in Chapter 12. This data contains the lengths of eruptions of Old Faithful Geyser in Yellowstone National Park, that's called duration, and the time until the next eruption interval for 222 eruptions from 1 month. And we want to know what the data tells us about the relationship between the length of the eruption and the amount of time until the next eruption, which might be helpful to tourists. Can we make good predictions? How accurate are those predictions? So the instructions for doing all of this is on here. I'm going to go ahead and just go through this process. So when you log on to StatCrunch and you go to My StatCrunch, then we want to go to Open StatCrunch and open a new StatCrunch page. Go to Data, Load from the file on my computer. Now you should previously have downloaded the Excel file that contains all this data from Canvas onto your computer. So I'm going to go to the file, and the file is called Old Faithful Data here. This is the one I have. I'm not sure exactly if I wrote Old Faithful Data TPS, but whatever, it'll be the one that you get from Canvas. And then you just scroll all the way down and push Load File. Okay, so I have all this data here, and now I want to do a regression. So go to Regression, Simple Linear Regression, and I select duration as my x variable and interval as my y variable, and I want to do make a fitted line and residual plot, residuals versus x values. I think that's all I need to do. Okay, and compute. Okay, so we first get our regression information over here, and this gives us our dependent variable, independent variable, gives us our equation, interval, and we're going to write that as interval hat. Okay, so there's the equation we're going to be writing. It tells us sample size, correlation, all this kind of information that we're going to be talking about when we write, use our vocabulary from Chapter 3. And then here's the actual, oh, I forgot to do one other, I thought I had my fitted plot. Okay, forgot to do one thing. So if I go to data or stat and regression and simple linear, let me do this again very quickly, sorry. When I went down to here, I did fitted line plot. I forgot to hold control. Select more than one by doing control click or shift click. So when I did residuals versus x values, I needed to hold down control so I would get both of those graphs. So here we go again. So now we'll see our results and two graphs. There's our scatter plot with a line through it, and there's our residual plot. Okay, so anyway, you should have all this information now, and now we're going to write about it. So let's go back to our file here and look at what we've got. Okay, so write the equation of the regression line. So there it is. Now we want to interpret the slope of this line. So here's the slope that's multiplied times duration, and here's how we interpret this. For every 1 minute increase in the time of the eruption, okay, so we're saying as x goes up by 1, what happens to y? The interval of time, that's y, until the next eruption increases by an average of about 10.36 minutes. Okay, so remember, notice that we're saying as x increases, y increases, positive slope. We say that for every 1 unit increase in x, we have the slope tells us the number of units of increase in y, and this is an average, and this is we need to use a weasel word because this is an approximation, because our regression line is always an approximation for the data. It doesn't tell exactly what the data is going to do. So that's why we need to say an average of about this. Now, the y-intercept tells us how much what the value of y is when x is 0. So it says for an eruption lasting 0 minutes, the duration to the next eruption is about 33.97 minutes on average. This does not make sense in the context, because if we have an eruption lasting 0 minutes, then we're not counting any sort of interval until the next eruption. Another way you can say this is for every 1 minute increase in the time of the eruption, the regression line predicts an increase of an average of about 10.36 minutes. Okay, next, we want to click on any row of, when it talks about our residual plot. So we go back to the residual plot, and I keep clicking the wrong thing. I want to go to that. There we go. So the residual plot, basically, if we click on any row in the data, then it will highlight the corresponding value in the table here. And then if I just push clear, it'll clear it off. So it'll make it pink. So I can, here's another one. There's another value. So we're going to, I have a specific one that I put on here that I want you to interpret. So if in row 7 it says the residual is negative 7.7906 when the duration is 2.3. So first of all, how do we calculate a residual? The residual is the difference between the actual y value and the predicted y value. So actual minus predicted. So first of all, we have to find the predicted y value for x equals 2.3. We use the equation to do that. So put 2.3 into the equation, you get y is 50. We know the actual value is 50 because that's on the line. If you actually look at the line, it says 2.350. So the actual y value is 50 when x is 2.3. The predicted is what we get from the equation. That's 57.7906. Subtract the two, and since the actual value is less than the predicted value, we get a negative residual. So that's how you calculate it. Now, what is the meaning? Excuse me for the yawning there. It is kind of late. For the meaning, it means during the 7th eruption, which had a duration of 2.3 minutes, the predicted interval of time until the next eruption was 7.9 minutes higher than the actual time. Okay? Or we could have said the actual time was 7.79 minutes less than what's predicted. Actually, that should be 7.8, not 7.9, because it's negative 7.79. So that should be 7.8. Okay, what does R, the correlation coefficient, tell us? Well, R is 0.877 if you go back to the regression output. The correlation tells us how closely the data fits to the regression line. If R is exactly 1, then that means that all the data is right on the line. So since it's fairly close to the line, to 1, it means that the data fits fairly closely to the regression line, and the association is positive since R is positive. Interpreting R squared, well, R squared is the square of R. So if we took 0.877 and squared it, we get 0.7695. But you don't interpret it the same way. The interpretation of R squared is that about 77% of the variability in the time intervals, that's the variability in Y, variability in the time intervals to the next eruptions, can be accounted for by its linear association with the length of the eruption. Okay, so if we were to look at the equation or the scatter plot here, let's look at the scatter plot. Oh, that's the one I don't have the scatter plot on. So let's do this, kind of expand it out a bit, and let's look at the scatter plot. Okay, so we're saying that as the duration of the eruption increases, it looks like there is also an increase in the length of time until the next eruption, on average. But there's also variability. So it's not a perfect relationship. But what we can say is that about 77% of the variability in the time intervals to the next eruption, the y value, can be accounted for by the linear association with the length of the eruption. In other words, the eruption does a pretty good job of explaining, the length of the eruption does a pretty good job of explaining the variability in the time until the next eruption, but not totally. Okay, now 6.15 is called S in the regression output. So if we go back and look at our regression output, you see this S right here, estimate of error, standard deviation. Now, in most of the computer outputs will say, it'll just say S equals. It won't say this wording. So when we see that S, then that number tells us the standard deviation of the residuals. Standard deviation then can be interpreted as the typical amount of variation. So the typical amount that the predicted interval to the next eruption varies from the actual interval is about 6.15 minutes, because a residual is the difference between the predicted y value and the actual y value. So it's typical, the typical amount of variation in that is about 6.15 minutes. So if we go back and look at the residual plot, we'll see that for any one value of x, so like 4 minutes, the duration, if the duration was 4 minutes, then we can see that the residual for that duration varies. Okay, so there's a variation in the amount of the residuals from what we expect. If there's 0 residual, that would be these values right here. They don't vary at all from what is predicted. So the typical amount of variation from what is predicted, we notice that it varies anywhere from about -15 to +15 minutes. So we see, and most of them are clustered more towards the center, so the typical amount of variation is about 6.15 minutes. Okay, so the next thing, is eruption a good predictor of wait time until the next eruption? Okay, so we want to look at how much variability there is. The standard deviation of the residuals is about 6.15 minutes. About 77% of the variability in the time intervals to the next eruption can be explained by the duration of the eruption. So that seems like it's a fairly accurate, based on those two pieces of information, it seems like that eruption is a fairly good predictor of wait time till the next eruption. So you're going to want to refer to particularly to R-squared, and then also perhaps to the standard deviation of the residuals to answer that question. Okay, so with those with this vocabulary review, now we are ready to move on to inference for regression.